This is the third lecture on reacting systems. We continue where we left off from last time, where we had defined what type of a system we have developed, how we are going to approach it, and now we will go into the analysis of that and begin to answer the question that we were posing in terms of what is energy release and what is the type of temperatures that we get. So, we write that same equation that we were looking at earlier, the burning of methane in air is a stoichiometric reaction. We have defined what is stoichiometric mixture, what is equivalence ratio, what is percent excess air, all those quantities we have defined. So, instead of this hydrocarbon could have been any other hydrocarbon. In this, the second reaction is for butane, and only reason for putting it here is that first out here what we are seeing is that number of moles need not be an integer, as we are seeing here it is fraction, and we do that so that the number of moles on this side for the fuel, this remains 1. That is one thing. The second thing to note here is that C4H10, which is LPG, the main constituent of LPG in the cylinder, this is in the liquid phase, but then when it burns, this is in the vapor phase. Another point to note is that this H2O, which is say in the domestic burner it just goes out as H2O vapor, we do not see it, but if you have put the gas flame low and put a vessel of cold water, you will see some H2O condensing outside it. So, this could be that the H2O leaves the reacting system, the device, in vapor form, vapor phase, or in liquid phase. We will see the implications of this on energy that is released by this reaction in a few minutes. So, what we want now is that we want the properties of the reactants and the mixtures to answer the question that we are posing, like heat release, temperature, maximum temperature possible. We will develop this analysis for two situations, open system and a closed system. And as we have already convinced ourselves that we will treat the reactants as a mixture, which is at equilibrium, and we will then put all the properties of a mixture that we have learnt earlier, all the parameters, the symbols, everything that we have already learned. This is what we will bring into our use over here. Then we will always write the reaction so that you have 1 mole of fuel, simply because everything else becomes easy, and we will often refer to various things, particularly energy release rates, on a per fuel kg or per fuel mole basis, per fuel mass. So, we will keep the fuel as 1 mole, and as we have seen, that does not matter whether this reaction, it does not tell us whether the fuel is stationary or it is moving. The reaction is applicable to both cases, where the whole system or the flows, there is no flow taking place, which is a stationary system, or there is a flow system, that is also okay. The reaction remains the same, the analysis remains the same. So, going back to our mixtures as well, how do we quantify our reactants and products? And this is exactly the same of what we had defined earlier in mixtures. Mass fraction of every species is capital Y I as the mass of that species divided by mass of the mixture in a given system, that the volume is fixed. So, we have same volume and same pressure and same temperature. Mole fraction for the same conditions, the number of moles of the species I here divided by the total number of moles in the mixture, and in both cases these are normalized things. So, the sum of all the mole fractions is 1, and this thing is also 1, and these two are related to one another, that the mass fraction is mole fraction divided multiplied by the mass molar mass ratio, and the opposite there in this case. And an important thing that comes out is that the mixture molecular weight is summation of the molar fraction multiplied by the molecular weight of that species, and this is summed off for all the species, which in the case of reactants we will denote by I, and in the case of products we will put J as the here and all the species in the products. Later on in the calculations, this becomes something quite easy to use. Sometimes we will be also using this one. Then in mixtures, we also define that the specific enthalpy of the mixture can be defined as the mass fraction multiplied by the specific enthalpy of each component, summed up over for all the species in the component. This could be either I, or as we said, this could also be J. On a molar basis, the specific molar enthalpy is summation of the molar ratio multiplied by the specific molar enthalpy, which we denote by a bar. So that's how we get the enthalpy of the products or enthalpy of the reactants. And now we look at specific entropy of the mixture. For a given temperature and pressure, this is the sum of the mass fraction multiplied by specific entropy at the temperature, but the pressure for ith species is its partial pressure in that mixture. So that's a difference here, that the mixture specific enthalpy is at T and P, but the species specific enthalpy is at the same T, but at the partial pressure of that species in that mixture. And we can express this in terms of a molar specific enthalpy, which you put a bar there, and this is SI bar, and this is the molar mass fraction. And we note that the specific entropy of any species, or in general a specific entropy for T and P, is specific entropy at T and a reference pressure minus R ln Pi upon P ref. So, we need a reference pressure for defining the specific entropy, and we have said that if this was ambient as 1 bar as this reference pressure, we had got terms like S0 bar, and from there we could get everything else. The molar definition of specific entropy is given by this relation, which is nothing but the same one, SI bar at T and P ref minus the universal gas constant and the logarithm ratio of Pi over P ref. So, this is all what we have already got from mixtures, and we know that if we have a mixture of molecules, how to get H, U, S, all these properties. Let us now start by looking at a closed system, and we will do two things: apply conservation of mass and then the conservation of energy. So, the first thing is a closed system. There is no issue of steady state because it is stationary, and we apply the conservation of mass to this. So, the equation there is straightforward from the mixture thing. We say that whatever mass was there before the reaction took place is exactly the same after the reaction. So, we write that summation of all the mass of every species from I equal to R, which is for every reactant species. This is equal to the summation for every product species, where J is the product, and these two are equal. So, this is mass conservation, and it is different from the mixtures that we had done where there was no reaction, because in that case we said that the mass of individual species is also conserved. Well, that is not the case here, because there is a reaction taking place. Some of the species here got disappeared and they do not exist in the products, and new species have appeared in the products which did not exist in the reactants. So, species conservation, though it can be written, you will have to write that the fact that there is a source term or sink term where the species has disappeared. We will not bother to write it at this point of time. In the case of our example, which was the methane air reaction, we have mass of methane plus mass of oxygen and mass of nitrogen. All of this is the reactants. And on the product side, we will have to have mass of carbon dioxide, mass of H2O, the water that is formed, and mass of nitrogen, all of which is the products, which is here. So, that is what this equation would become practically in solving problems, it will become like this. So, that is for conservation of mass, and now for this same system we look at conservation of energy. And we assume that there is no change in kinetic and potential energies, and so we can write the first law equation as q from state 1 to state 2 is work done plus u2 minus u1, and it is a closed system, and for the time being let us assume that there is no work transfer and we put this at 0. u2 is at some temperature and pressure, and this is nothing but the condition of the products, and u1 is nothing but the condition of the reactants. And as we said, reactants and products, each one of them individually can be analyzed as a mixture of gases. And U, as we have learnt earlier in the course, is H minus PV. The reason for writing this is that we have tables and data for H in many cases. U is not tabulated, but that is the way to get U. So, now let us write down this reaction further and see what happens. We can say that Q12 is Hp minus Hr minus pressure product of PV for the products minus the same product, but now for the reactants. And now we expand the equation we had just put a few minutes back, that the extensive property enthalpy of the products, this is summation of enthalpy of the individual species, which is Mj Hj, and J is taken for every product. And similarly, Hr is summation for every species for Mi Hi. Instead of writing in terms of mass of the individual species, we can also represent this by the number of moles and using the molar specific heat, number of moles of I multiplied by the specific enthalpy of I. So, both these bracket terms can be made into this form. So, in this case, if suppose this mixture was methane plus air, then the reactants, we will have to get the H here, or H bar for CH4, say H bar for O2, H bar for N2, and all of this will be at the state at which the reactants are, which could be Tr and Pr, or if it is state 2, we can say that this is T2 P2. So, this is what the products were. For the reactants, for the products, so this is the reactants, we have H bar CO2, H bar H2O, H bar N2, and this we evaluate at the temperature and pressure at which the react of the products. So, these are reactions. This will be T1 and P1, this is T2 and P2. So, the reactants are at temperature T1 and P1 and products at T2 and P2. So, what the problem has now come to is that if we know these enthalpy values, we can then put them here and calculate what was the heat transfer during the reaction. So, how do we get these? We will come back to this question in a few minutes after looking at open systems. So, first the open system conservation of mass is the same type of system that we had made earlier, where we had inflows of the reactants and outflow of the products. And we apply the conservation of mass for a control volume with the assumption that there is steady state. That means, mCV dt term that becomes 0. So, we are left with the fact that mass inflow rates is equal to mass outflow rates. So, inflow rates are given by m dot I, where I is every species in the reactants, and this has to equal the mass flow rates of every species that is flowing out with the products. Again, as before, some of the reactants disappear, new species appear, and so species conservation is not strictly the way we are writing this. And in the case of the, if this was the fuel was methane and going with air and coming out as carbon dioxide, water and nitrogen, then we would have to need mass flow rate of CH4 plus mass flow rate of O2 plus mass flow rate of N2. This is what we have in the reactants, and for the products it will be mass flow rate of carbon dioxide plus mass flow rate of H2O plus mass flow rate of N2, and this is all the products. So, that is one part of the story, and now we look at the same system and look at the conservation of energy. And we assume that in most of the systems, and with a reasonably good assumptions, that we have steady state, that kinetic energy changes and potential energy changes are 0, and we also further assume that work done is 0, work transfer during the process, but there could be and will be heat transfer. So, the whole energy equation now becomes Q dot C V plus m dot I H I, where I is every reactant species. This is equal to summation of the same product for every product species. Alternately, we could write these as mass flow rates of the moles multiplied by the molar specific heat, molar specific enthalpy. So, for the methane air reaction, we have to have m dot of CH4 multiplied by HCH4 plus mass flow rate of oxygen and specific enthalpy of oxygen, mass flow rate of nitrogen and specific enthalpy of nitrogen. This is mass flow rate of carbon dioxide and specific enthalpy of CO2, mass flow rate of H2O and specific enthalpy of H2O plus mass flow rate of nitrogen multiplied by specific enthalpy of nitrogen. So, this is all our reactants, all of these are our products. And again, now what we see here is we have to get these terms, the specific enthalpy of each of these and specific enthalpy of these. That is the issue before us. So, now we got the same question when we looked at the closed system. There also we needed these specific enthalpies. So, what is the issue? Well, we have studied in properties of a pure substance that you had tabulated specific enthalpies. First, in reacting systems, we got so many substances that maybe we do not have the tables data for every species. It may be there, but not be readily available. Second, there could also be some radicals in the certain chemical reactions for which data is not there. The next thing to note is that while pressure, volume, specific volume and temperature are absolute quantities, in the sense that they do not depend on the reference state, and the meaning for them is same for every substance. So, there is no ambiguity in it. So, this is common to all species. So, universal, and this is applicable to all species at all states. But as we saw with pure substance, specific enthalpy and specific internal energy and also specific entropy were all with reference to a particular state, which we called the reference state. For water, the reference state was that the specific enthalpy of saturated liquid at the triple point is 0. It was completely a choice of convenience. For some materials, it was that instead of 0 degrees, the temperature was minus 40 degrees Celsius or minus 60 degrees Celsius. In the case of the psychrometry chart, the reference state was different. So, although we were getting values of H, numerically their values would be all different, which was all fine if you are only looking at a system with one pure substance. If you are looking at a mixture, we realized that the reference state for both the substances must be the same. Now, we have an issue coming up here that H, U and S have different reference state for different materials. For ammonia it is something, for carbon dioxide it is something else, H2O itself somebody could have some value, somebody else would have some other value. And the reason why everybody does not use 0 Kelvin as this fixed reference state is simply because all the numbers become very large, and we say, well, we do not want to deal with very large numbers in most day-to-day calculations, so we will shift our scale. It is a matter of convenience there. For S, we developed a standard state entropy definition S 0 bar, and that took care of much of these issues, but not for H and U. The second complicating factor that is coming into this case is that we have reactions. There are many species in this, and we have mixtures of these species. And in order to calculate H and U of a mixture, we have a very important requirement coming up, is that we should have the same reference state for each species. Otherwise, we could end up in a big mess. So, what this means is that while the earlier property data were there, we are now going to shift and change and relook at it in a different way with a reference state which is unique, unambiguous for all species. So, this is what we have to define the specific enthalpy for. There is one more issue that is coming up in the case of reacting systems, particularly combustion, is that all these properties that we had for properties of a pure substance were for temperatures in a particular range. In combustion, we get much higher temperature than we saw in those cases. Temperatures of several 1000, 2000, 4000, 5000 Kelvin or even more are not uncommon, and most of these property tables do not go anywhere near these temperatures. So, we need property data that goes up to this high temperature, that is one. And second, at these high temperatures, the pure substance also undergoes a change in that there could be some dissociation. So, that also needs to be taken care of, and so we need a completely different set of properties that firstly are consistent across species and go to much higher temperatures, and from that we can do our combustion calculations. So, the first thing we do is define a reference state, and we say that for all enthalpy referencing, we will use 25 degrees Celsius, which is 298.515 Kelvin as a reference temperature, and the reference pressure we will call it as P superscript 0 is 1 bar or 0.1 megapascal. And then we will say that we are now going to redefine our specific enthalpy, and instead of working with a mass basis, we will from now on all the property data we will get is on molar basis. So, H I bar T, where I is any particular species, this is what we are calling as all the enthalpies that we were looking at earlier. What we said was H I or H I bar is this now, and this multiplied by the molecular mass of I species will give us this. So, the two are very easily converted, and we will concentrate on this part. And to be explicit and say that this is enthalpy at a particular temperature for a particular species, this is the expression we are going to use. So, this is what we will call standardized enthalpy, standardized molar enthalpy for the ith species Hi at T, which is a function of temperature and not of pressure. So, that is HIT bar. This is standardized molar enthalpy. And this we will express as sum of two properties. One we call H0F, I is the species and at a particular reference temperature, plus delta H, and which is a change. So, what we are saying is that at this temperature we have a particular value of a fixed enthalpy to which we add a change in enthalpy from that reference state to the actual state. So, actual state is T, reference state was 25 degrees Celsius. So, this with a F subscript is enthalpy of formation at standard state. So, this is a new term that we are now introducing, enthalpy of formation at standard state, which means this was done at T ref and P 0, and all the property data that we have will be for this condition 25 degrees Celsius and 1 bar. So, this is like a fixed parameter that at about some reference temperature it is T, the enthalpy is fixed, and this is now made consistent across all species. And then there is change from the reference state temperature to the actual temperature T. So, either it is we call it T, or this is from T ref to T. So, this is the sensible enthalpy, what we are calling subscript S. Sensible enthalpy change, and in some cases you may just see enthalpy change in going or transiting from the reference state temperature T ref to the temperature at which we need the property. So, this is a new thing that has come up. Enthalpy of formation is something that has come as a new thing, and we will look at this in much more detail in a few minutes. So, now we can write the same expression in a little more convenient way. Is for any species we can then put the subscript I. So, we have dropped that I for the time being and says that the molar specific enthalpy at temperature and pressure is molar specific enthalpy of formation at standard state plus change of enthalpy from standard state to the actual temperature and pressure, where this part is the enthalpy of formation. And you can rearrange these terms and say that delta H for this change is delta H at T, and we can say that the effect of pressure on specific enthalpy is not very significant, minus the enthalpy of formation at 298.15 Kelvin, or somewhere you will see only 298 is written, somewhere it is 25 degrees C is written. So, this is something we are getting, and the convention that is followed and it is consistent is what we have written in the next statement, that the enthalpy of formation is 0 for the elements in their naturally occurring state at reference state temperature and pressure, which is 25 degrees C and 1 atmosphere. So, at 25 degrees C, 1 atmosphere, oxygen exists as O2, a diatomic structure, and we say that enthalpy of formation of O2 at 298 Kelvin is 0. So, instead of oxygen we are looking at nitrogen or hydrogen, this would be the same case. So, what it means is that having set this as a reference state as 0, we can now go and ask the question that if I have to break oxygen to form O plus O, or you look at O2 becoming O plus O, or O plus O becoming O2, what is the energy involved in this? In the first case, if we have to go like this, the bond which is the O-O bond, this bond has to be broken. For that you need to give energy, and that is called the bond dissociation energy for oxygen. And this is known to be from data tables as 498,390 kilojoules per kilomole of oxygen. So, when you give that much energy to 1 kilomole of oxygen, we produce 1 kilomole of O plus 1 kilomole of O, 2 kilomoles of O. So, the enthalpy of formation of atomic oxygen O at 298 Kelvin is half of this value, which is 249.15 kilojoules per kilomole of O. So, now we have got something. The enthalpy of formation of atomic oxygen is known, and like that we can get the enthalpy of formation for every element like this. So, we can have N, we can have H, O is already there, we can add more chemicals to it. And then, so you can even add say C like that. And then what one can do is select, in this case, if O and O were to be combined, we knew how much energy would be released. We can then say, if I have to combine C and H and H and H, I have to create 4 bonds, what is the amount of energy required? From knowing the formation enthalpies of individual atoms, we can get the formation of any complex molecule, all referenced to the same state. So, we have a consistent method of getting the data. So, where do we get this data? First, we need the enthalpy of formation, and then we need the other part, which was delta H bar going from standard state 298 K going to T. So, how do we get this data? For this, we now start using yet another set of property tables, where they have listed these different things, and I will show you the tables in a few minutes. The first column has the temperature in Kelvin, the second column gives the molar specific heat, the third column gives what we have been talking of here, delta H, which is H0 T minus HF0 at 298 K. That is molar specific enthalpy at temperature T minus enthalpy of formation at the reference state. That is the third column. So, this is one column, second column, third column. The fourth column gives the enthalpy of formation at that particular, at any temperature T, and in this we will have various numbers coming down, then S0 T, and then finally Gibbs function for formation, GFT. In this temperature column, there will be some temperatures below, and then finally every one will have one common temperature 298 K, and then it goes there. And so, if you look at HFT at 298 K, this is the value that we are looking at to put over here. So, this value we can say is propping up into this part. From here it comes. So, you look at 298 K, pick up this value, it goes into this expression. And then we can use the same relation, that enthalpy is this plus delta H. Delta H came from here. So, we can write this even on the top of this. This is delta H bar going from 298 to T. So, look at that, we will have a look at the tables now. These are available as standard data. Okay. So, I mentioned these are standard data tables, which have been generated from statistical mechanics and kinetic theory of gases, and this is here is given for oxygen O2, is molecular weight 31.999, enthalpy of formation at 298 Kelvin kilojoules per kilomole is 0. So, the first column is temperature in Kelvin, starts at 200 Kelvin, and this table ends at 5000 Kelvin. So, we are looking at this temperature going from a low value 200 K and all the way it goes to 5000. That is a much higher temperature than what we have looked at in the properties of a pure substance. And that is required because in chemical reactions you do get these type of temperatures. The second column is the specific molar specific heat at constant pressure. So, this is Cp bar and it goes in this column, and you can see that specific heat increases. And this is one of the important things of this table, is that unlike all the earlier calculations that we did, quite often we assume that specific heat is constant with temperature. We see here that there is a substantial change in the specific heat, it increases as the temperature increases. So, constant pressure specific heat is only an approximation. You would actually, if you integrate for enthalpy integral Cp delta T, you will get a much more accurate value, and that is what this table does. Then you have this column here, this is H0F at any T, and here at second temperature you can see is 298, and for this the value here is 0. And you can also see that delta H for this value, which is here, this is also 0. So, the second column was H0 at T minus HF0 at 298 Kelvin. So, HF0 at 298 K is this value that we are getting. This is what is coming here. And so, now this table gives a series of numbers, which is the difference of enthalpy minus standard state enthalpy, and that is what we get from here, and even at going down below this value you get minus values. This column is S0 bar at a temperature, standard state entropy, and finally here it is, we will see later on, G0 formation at any temperature, the Gibbs function for formation. Right now we are only interested in this and this part. So, that is where we are getting this table. So, if you go to this table, we get all this data, and we can pick up the temperature, get these properties, and if we are working with a temperature that is not listed here, but lies between two values, say between 2000 and 2100 Kelvin, we will have to do linear interpolation. Alternately, all these are now available as computerized property tables. One can always put the value there and get the exact value that you want. Calculations are now much easier. This has been programmed. So, now if that was for oxygen, let us see what happens for atomic oxygen. So, this is now O, molecular weight 16, enthalpy of formation at 298 Kelvin, 249.197 kilojoules per kilomole. Again, the columns are exactly the same. The difference now is that, yes, H0 T minus HF0 at 298 K, at the 298 Kelvin temperature this number is 0. But the formation HF0 298 K, which is there in the second column, this is a finite number, this is going there, it is non-zero. That is because this is the amount of energy that we got when we had to break the OO bond, and for O2 we had put the specific enthalpy as 0. So, the formation of a O atom requires energy, and that is what is showing up over here. Rest of it is very similar to what we have had earlier. And one more we will see, this is water. So, this H2O would come by taking 2 hydrogen atoms and 1 oxygen atom and making certain bonds, and the way to make those atoms was to dissociate from their natural state, for which the enthalpy was known, and then we find out from joining what happens to H2O. So, basically you can calculate this H2O's enthalpy of formation from the enthalpy of formation of its atomic constituents. So, what we have here is that again the same set of things is there. This is your delta H bar, and it says that enthalpy of formation at 298 Kelvin is minus 241.845 kilojoules per kilomole, and enthalpy of vaporization kilojoules per kilomole is 44,010. So, enthalpy of vaporization is nothing but what we have learnt in the earlier course, as this is in kilomole basis. So, this is H bar Fg, same number. So, what you have here is that the formation enthalpy of formation at 298 Kelvin for water is given over here, this is the value that will be taken in this calculation, and this is non-zero. And here again, after that the numbers keep changing, again the property data goes to 5000 Kelvin. So, this is our way to get all the property data that we have been looking for in doing all the calculations, that when we wanted the value of H, this is how we get it from this and this table. The values are different simply because the reference state is same, and enthalpies, a difference of enthalpies in any two states will be the same whether we use the earlier tables or we are using these tables. So, to summarize, how are we getting the specific enthalpy for any species I, and the subscript I has been dropped from here. Method 1 we have just looked at is the use the tables, or it could be computerized programs or interactive software, that does not matter, which is H 0 at t, which is H f 0 at t into 298 k plus average specific heat T minus 298. So, that is one way to do it, but this is of course the approximate way. The correct thing would have been to say that this is integral of Cp 0 t from 298 to t, approximation is this, the exact value of this integral is what is there in the tables. So, that is for some quick calculations one can do this, is to use Cp average Cp value over that temperature range 298 to T. So, this is over 298 K to T, whatever was in Kelvin, some sort of an average value. But the tables what they gave us is H 0 of T, this is equal to one column data that we read, H 0 of T at bar minus H f 0 T at 298 plus H 0 F bar at 298. And to get, this is all molar basis, mass basis, this is H 0 bar at T, which came from here, multiplied by the molar mass of that particular species. And so, we can do this for each species. This could be either in the reactants or in the products. For phase change, we will do that H 0 F for a liquid. In fact, in the bracket this I left it blank, because now F has got two meanings coming up here, and so it is causing confusion. I will come back to it in a minute. This is H 0 F, which is the formation in the vapor phase, minus H bar F g, and this is where you can see the confusion coming in. We are using now F g from what we have learnt in properties of a pure substance, where F is saturated liquid and G was saturated vapor. But now, F is being used in this case as formation. So, what we are saying is the enthalpy of formation of saturated liquid. So, ideally this F will be F and this will be a G. So, just to minimize the confusion, I have put different colors on it, but that is one of the problems, that we have same subscript appearing for two different things, but does not matter. We keep our bookkeeping straight, that this F means that we are looking at saturated liquid, and this means that we are looking at saturated vapor. H f g bar is nothing but your H f g is H f g bar times the molar mass of that particular material. So, two are exactly the same. So, numbers, values and all the same as what we had earlier tables. So, now we come to the last part of the lecture. We have now developed all the tools that we required to do any analysis of the system. We will now use those for a few specific things to learn about a particular reaction and for a particular type of fuel. And these are important numbers that we look at and come across quite often. So, for any general reaction, the first thing that we would like to talk about is what is called enthalpy of reaction. In the case of a reaction being a combustion reaction, we are looking at enthalpy of combustion. So, what we are doing is the same thing, but we are now looking at a steady flow reactor. That means, you have steady state, you have the reactants going in and the products coming out, and there is some heat transfer taking place. So, in defining the enthalpy of reaction, or we will now start calling it enthalpy of combustion, is that the reactants are going in. Firstly, it is a stoichiometric air fuel ratio, that is number 1, and second, they are at standard state conditions 298 K and 1 bar. And what comes out is next, first, that there is complete combustion, and it is a stoichiometric mixture anyway, and the products are also at standard state conditions 298 K. So, this went in at 298 K 1 bar, this came out as 298 K, which can be only possible when there is heat transfer out of this system, Q dot C V. So, when we write the first law, it is Q dot C V plus m dot I H I for the reactants equal to summation of the same thing for the products, or Q dot C V is what was H summation for products minus summation for the reactants. And this can also be represented as H dot for the products minus H dot for reactants. If we do it on per mass basis, we divided it throughout by mixture mass flow rate. So, the mass flow rate of going in and coming out is going to be the same, with that is not an issue. Q dot C V over m dot mix. Now, remember, m dot mix is same as m dot P, which is same as m dot R. This we call is delta H R, enthalpy of reaction or enthalpy of combustion, which is H of P minus H of R. Now, remember, P and R are mixtures. So, these have to be get from mixture properties. Or delta H R is H P minus H R. So, if you have expressed this as a total one, or this was a mixture thing, then delta H R is kilojoules per kg of fuel, is this value divided by molar mass of the fuel, or per kilogram basis, delta H R is kilojoules per kilogram of mixture, which is delta H R upon this into mass flow rate of fuel over mass flow rate of mixture. So, this is more common one to be found, and this is what we use, is how much kilojoules is released per kilogram of fuel. That is the thing that we are always interested in, and that is the way to get it. We are not going into the full details of it, because now we know how to get H P and how to get H R from the summations, and then using delta H and H formation. From there we can get all these numbers. A small change that can be done over there is that mass of fuel over mass of mixture can be rewritten as 1 upon air fuel ratio plus 1. So, this is a connection that we can put there with the heat of reaction. A common term we use in defining fuels is the heating value or the calorific value. So, we say heating value is nothing but heat of combustion, and this is not enthalpy of combustion. This is now heat of combustion, delta H C, or the heating value is nothing but numerically it is the same as heat of reaction, but of opposite sign, exactly the same, there is no change. The only complication or variations that come into it is that the heating value could be defined as higher heating value or lower heating value. Higher heating value means after combustion the H2O is in vapor state, and this is in liquid state, because when H2O condensed, that also energy was taken out from the system. The lower heating value is the one that you have when H2O stays in the vapor phase. So, that enthalpy of evaporation or condensation is not available to be taken out from the system. We would also like, you should also keep in mind that another thing could happen, that the fuel itself, as we had mentioned earlier, it could be in liquid phase or it could be in vapor phase. If it was a liquid, it will take energy to become a vapor, and then the chemical reactions will start. So, the enthalpy, the heat of combustion from a liquid fuel will be less than the heat of combustion of a vapor fuel, whether it is HHV or in both cases. That means, the water vapor condition is the same, but this will be less than this value. Just to recap what we had said earlier, delta Hc is minus delta Hr, which is Hr minus Hp. Enthalpy of reactants is number of moles of every species in the reactant multiplied by the molar specific enthalpy, and this we have already learned is a new thing that has come about. This was H0F at 298 minus delta H bar in 298 to T. This is what we got from the tables there. So, this is what we had wanted. So, we get this plus we added the particular values to it. So, this is H, basically what we are looking at, H bar at T. So, these two are the same. Now, we look at another condition where the combustion, instead of taking place at constant pressure, which is what we had looked at in earlier case, now it takes place in a closed system, which is at now constant volume combustion. So, now U r, which becomes now the internal energy of combustion, is U p minus U r, and this we can now write as I is equal to P N I into H 0 F plus delta H minus P v for each species. And this is at the product state. And a similar expression we can write for the reactants, N j H 0 F plus delta H bar minus P. This was the initial pressure, this is the final pressure, specific volume at J. So, what did this, we can then simplify this and write it in terms of the specific enthalpy, H p minus H r minus these two terms going in there, which is summation P final V for J minus summation P initial V for each reactant product. So, I is every product, J is every reactant, and from there we get that U bar R is H bar R, or we had called it delta H R minus R u T times N p minus N r, and these are in gaseous phase. So, the internal energy of combustion could be very different from that of the specific enthalpy of specific enthalpy of combustion. Finally, we ask the question, what are the temperatures that we can get, and in particular we ask the question, what is the maximum temperature we can get from a reaction, and that is called adiabatic flame temperature. So, if we say that I have a fuel and I am burning it with air, we now will develop a method. We say that this is the maximum possible temperature you can get. If you burn it with oxygen, this is the maximum possible temperature you can get, and that sets an upper limit to all the energy conversion machinery that we design and the systems that we design. By burning a fuel, you cannot get a temperature greater than that. That is an upper limit. So, we look at constant pressure combustion, which is an open system control volume type. Q dot Cv is equal to 0. That means it is adiabatic, no heat transfer from the system. So, we have a reactor into which things were flowing in and flowing out, and this was perfectly insulated. So, all the energy released by combustion went to increase the temperature of the products. So, which means that HR of the reactants at T inflow temperature and pressure is enthalpy of the products at adiabatic flame temperature and the pressure. So, this we can say is T adiabatic at constant pressure. So, that is one way to define it. The other way is constant volume combustion, where Q12 is 0, and now the two internal energies are equated. And if you convert that into terms of the enthalpies, you get HR minus HP minus something else, and this is equal to 0 because this is equal to this. So, this basically tells you in both cases the T final temperature that the system will get is the adiabatic flame temperature. In this case, it is constant volume, and we can see that because the system did not come back to its original pressure, the adiabatic flame temperature at constant volume will be adiabatic flame temperature at constant pressure. But in practice, producing a constant volume continuous process is not entirely possible, and so most common referencing of adiabatic flame temperature is at constant pressure. So, this is what people would normally talk of. Say a gas turbine, it is a steady flow process like this, and the adiabatic flame temperature is at constant pressure. So, how do we calculate that? We have written those expressions there. We can now just write down all the other, for the constant pressure case, m dot I H I, this is equal to summation m dot J H F J I, and then we can equate these and get that for the inlet state this becomes n dot 1 H 0 F 1 like that, and for the reactants this will be H 0 F plus delta H bar at T adiabatic for each J species. And then we have two options, either we use the tables or the programs and to calculate the T, in which case you assume a T, then from there from the tables you get you calculate HR, and then see if that HR matches with the enthalpy of the products. If yes, then that temperature is the adiabatic flame temperature, otherwise iterate. Or we can even have a computer program that does the iteration for us, we do not need to do it now. Or the other case is an approximate solution, does not require iteration, it is quite simple, straightforward. We can say that delta H for going up to T adiabatic, this is approximately equal to Cp 0 into T adiabatic minus 298. So, we are assuming a constant specific heat over this range of T adiabatic to 298. And we can calculate T adiabatic without doing any iteration. It is easier calculation, but it could be off by at least about 100 Kelvin, and usually it will be under predicting the actual adiabatic flame temperature, and that is because this is an approximation. The tables would give the exact value. So, that brings us to the end of the thermodynamics of reacting systems, where we learnt how to take the laws and the concepts that we learned for a pure substance and apply it to a reacting system. We looked at various applications and realized that thermodynamics is one aspect of a engineered combustion system, which has got fluid mechanics, heat transfer, and many other considerations coming into it. We then made a simple system out of it, and we said that we will only look at the reaction as a device or some sort of a black box in which all the micro details are completely subsumed, and we are only worried about saying that what we have is reactants, and they go through a process and they become products. We made that model. After that model, we applied the conservation equations, conservation of mass and conservation of energy. And in doing the conservation of energy, we came across the need for how getting enthalpies for different species and referencing them in a consistent way to a standard condition. So, we came across the use of a new set of tables which are consistent in this respect, and for reacting systems we have to use those tables. And using this, we then came across various definitions of the reacting system alone. We came across air fuel ratio, which is at the gross level, fuel air ratio, equivalence ratio, and then percent excess air, like that. And finally, we saw how from all these reactions we can get the enthalpy of combustion, then heat of reaction or heat of combustion, and finally we said what is the maximum possible temperature, for which we got the answer by way of a adiabatic flame temperature. Or just the adiabatic temperature. So, with this we are now able to do a macro level analysis of a combustion system, and that is good enough to do many calculations of use. So, this forms the basis of how combustions happen, but as we have seen from the actual devices, things are much more complicated, and to actually understand those, one has to go to a advanced course, which is a postgraduate course in combustion, and then we begin to look at more and more realistic way how to design combustors or how to understand a combustor to achieve things like minimizing emissions. With that, we will complete this sequence of lectures on the reacting system. Thank you.